Welcome to part 2 of building machine learning library from scratch. In this video, we will be creating one of the most foundational and important class that the library will depend on. This class will be responsible to calculate gradients as well as perform backpropagation, and we will build it step by step without any external libraries. Let's start. So, first of all, I have included some headers that I think will be useful in today's lecture. Then I've also defined this class that I will just walk you guys through. And it's just a skeleton class we will build upon this. And in the end, I want to define this value A, value B, do some addition operation, get a value C. It's similar to what we did in our last lecture. So in the graph, it will look something like this. We have value A, we have value B, we do some addition operation, and we get a value C. And similarly, we can do subtraction operation, multiplication operation, and so forth. Okay, so we have this class value and we derive from this class. Any one of you who's not comfortable with the syntax, I can just give you a brief overview. We need to do this because we are using a lot of shade pointers, and where exactly we will need this, I will let you know once we reach that stage. But you can just think of it as that we are deriving from a shade from this class so that we can do some shade pointer operations, basically. Okay, so now that begs the question that why do we really need a shade pointer? The reason is that when our network grows a lot, we will run out of stack memory space. So we need to allocate memory on the. So that's why we will be dealing with shade pointers. I've created this type def so that we don't need to write shade pointer value again and again. And let's walk through some data members. First of all, I've defined a data member called data. And data is basically the value of the class value. So I know that's very confusing, but for example, we have a node A and that has a value of -1. So this data member represents that value of -1. Then the second data member is grad, that stores the gradient of that data member. The third operand is called op, and that contains the operator that was used to construct the current node. So for example, here, C was constructed using an addition operator, so we will store this addition operator here. And ID is something unique to that node, so we need a way to distinguish between nodes. So we just give it a unique ID. And the last of it is previous. Previous is a vector of value. So why we need this is here, for example, A and B were added to give C. So when we do backpropagation, we need to know what were my children. So children of C were A and B. Since I need to come back to them, I need to store that value. You can see that here I have this public create function that creates this value. It calls the constructor of value. So now you must be asking, why not we make a public constructor? The reason why we are not making public constructor is we don't want the clients of this library to directly call the constructor of value. Since value will be managing resources and will be doing a lot of important stuff, we need to expose an API for the clients to construct it rather than directly constructing. With that, we can ensure that value is always constructed correct. That's another technique that you can deploy when you're creating some software products. You need to create some APIs that the client uses, letting them use everything. Well, so we have this public function that the clients can call, create, and they will pass in the data and the operator, and we will just create a value class for them. So another data member that we want to have is a static data member called current ID, and current ID will start from 0, and whenever value will get instantiated, we will increment current ID, and whenever value will be destroyed, we will decrement current ID, and that will help us track how many nodes there are currently in this graph. And this ID will be equal to this current ID. So I can show you what I'm talking about. So for example, here I can also take a size D ID, right? And here I can just do current ID plus plus. And here I can say ID is right. So we always increment this current ID and pass it through. And to make it clear, you can do something like this. This should make it work. And another thing is, when we destroy value class, we need to decrement this ID. So we can just create a destructor pretty fast. So this is the destructor. We'll just decrement this. Okay. So having said that, let's try things out. So let's try to create a value. Let's say auto A is equal to value create, and we will pass it 1.0, and we will pass it, let's say, a string, and we will pass it, that's it. And let's say if we are able to compile it. Okay, so we have some undeclared, I would just forward declared things here. So I would just say, okay, let's try it again. So we have another error, and it says value create, call to non-static data member without object. Okay, so I think we did not make this a static data member. So just call it like this. And I think that should take care of it. Compile successfully, as you can see. And if we do this, there should be an object file out. All right, so once we are done this, that means we are able to instantiate A correctly. Now let's move on forward and see what do we need to do. So let's start by creating a add function, something like this. And every function that we will make will mostly be static because that's just a functional choice. You can make other design choices as well. For this, I'm just going with static because it makes it clear that what we are trying to do. So for example, in this function, it will make clear that we are adding A and B. And since this will not be directly be used by client, we will have some other APIs on top of it so that clients can easily use it. So let's create another class, and we'll just call it static, and we'll return a value pointer, and we'll just call it add for now. And it will take another value pointer that we'll just call LHS, and it will also take another value pointer that will be the right hand side. And we need to fill this function. So when we will call something like this, auto C is equal to add A plus B, A will be the LHS and B will be the RHS, and we need to return a C. So value pointer will be C. So if we compile it here, we will see that there is, let me zoom in a little bit. Yeah, there you go. So let's create two values, and B, and let's call it 2.0. Actually, let's call it, the operand will be null because these values weren't created using an operation. And yeah, that's basically it. So if we compile it, we get an error. All right, we haven't defined add. So that's what we have to do next. So let's do that. So first of all, when we do A plus B, we will get C. So let's say auto out, that we need to return from this function. It has to come from the addition of A and B. So that means we have to create a new value pointer. So that means that we will need to call this create function. So let's call value and create, right? That's the thing we need to call. And the data value will be the data that LHS has and the data that RHS has, and we add it. So, for example, if the data value of A is 1 and data value of B is 2, the data value of C has to be 1 plus 2. So, and the value and the create function takes the data as the input. So we need to do LHS dot data plus RHS dot data. And we also need to provide an operator. And since it's an add function, we will pass in plus. So that's the out value. And we can just turn it like this. And if we try to compile it now, let's try compiling it now. Okay, so since LHS is a pointer, we need to do something like this. There you go. We have able to compile it correctly. So we got C. So this is fine for propagation, right? We keep on doing this. So similarly, let's also make a multiply function. And let's call it multiply. And instead of plus, we will do this. And we will do this. And similarly, also make a subtract. And this will do this. Let's try some things out. So we have A and B. We add it. Let us include C assert also. C. These are private. I'll just make it for public for now, just to test things out. So C's data should be, any guesses? It should be 3, right? So that's our first assert. So let's see if that passes. And another thing that we need to make sure is that the C's operand should be plus. Let's compile it. Assertion should pass. So C's value is this, and everything looks fine. And similarly, you can check for multiply and subtract also. It should work fine. Okay, so let's talk about forward propagation now. So you have the C value, and now let's say you do auto D is equal to value multiply, and you say, let's do C, and then multiply C with C. Something like this. Okay. And D dot data, D dot top. So these data, C's data was 3, right? D's data will be 3 times 3. That should be 9. And D's operand should be multiplication, because D was created using multiplication. So again, we can test our theory. Okay, everything works fine. So that's good. I will also create a print function so that we know what's happening. And the way we can do is we can just do void print, and what this will do is it will print something like and gradient is 0. So we need to see if whatever we calculated makes sense. Let's print that out, and let's do, so there seems to be, yeah, we missed this. Okay, so we have data 9, gradient 0, and that's what we expected, right? So let's carry on forward. So one thing that you guys might observe is we don't store our children. So for example, D does not store its children, that is C and C. So D gets originated from C and C, so it doesn't store that. So we need some way to store that. We just assign it right here. So we assign the previous data members here, and the previous data members here will be LHS and RHS. So out was created using LHS and RHS, so we just do something like this. And we can do the same thing here. Same thing. So that's how we do it. And LHS and RHS are value pointers, and the previous here is a vector of value. So we need to change that. We need to store vector of value point. So that's basically that I think is needed. And if we compile it right now, compiles. So I think everything works fine. So while we are here, let's try to think it through. So we have A and B that gives C, then C and C, they both give D. And this will keep on going forward until and unless we calculate the loss. That's the final value of the forward propagation. So the final goal of forward propagation is to calculate the loss. After that, backward propagation takes charge, and backward propagation that will propagate all the gradients, it will do all the derivatives, and it will backpropagate those derivatives back to the input. So let's say C gave rise to a loss L. We will start with L and keep on going backward till we reach A. So now we need to do backpropagation. So let's talk about backpropagation now. So let's assume that you had A, B, you calculated C, you calculated L. So everything looks good in forward propagation. Now when you come backward, you need to calculate the gradients as we discussed in the last lecture. So you already know the value of DL with respect to DC. Now you need to calculate what's the value of DL with respect to DA. So how and when will you calculate DL with respect to DA? Because ultimately you need to find out how the loss changes with respect to A. So let's come here. In our backward journey, there will be a point when we will reach this node C, and at that point we would have calculated the gradients till C. And now we need to calculate the gradients of A and B. So the way we will do is we will create a backward function, and we'll just call that backward, and that will essentially be a lambda, and we will update the gradients of A and B here. So what we will do is we will give it some value here. We will update the gradients of A and B here. If you recall from our last lecture, the gradient of A is just equal to the outward gradients, that's dl by dc. So the gradient of A will just be equal to, we don't have a C, we have a out here. So it will just be equal to this. And similarly, the gradient of the RHS or B will also be equal to the output gradient, since it's an addition operation. And the other thing I would do here is I will just do plus equals. Plus equals is just because we want to accumulate all the gradients. So we don't want to wipe the old gradients. And the way we want to capture is using weak pointers. The reason we want to do weak pointers is we don't want to increment the reference count of the value when we capture by lambda, because increment the value of the reference count. So we don't want to do that. So we capture it by weak pointer. You need to lock it in order to update it. So it will look something like this. And here, this will be 1. We don't need to worry about this. And similarly, we can do lock, something like this. So this will be the backward function of it. I can explain it again. So let's say you're at point C, and now you want to calculate the gradients of A and B. So, and at that point, this function will get invoked, and the gradient of A is just equal to the gradient of C. Similarly, gradient of B is just equal to gradient of C. So that's how addition will work. Let's talk about multiplication. the formula will remain the same. So dl with respect to dA, that means the gradients of A, will be the local gradient times the output gradient. And the local gradient now will be dC with respect to dA will be the value B and times the output gradient. So if we look at multiplication, everything will remain the same. The only thing that will change is do something like this. And for RHS, we will do this will be LHS. So LHS will be calculated using RHS's data times the output gradient, and RHS will be calculated using LHS data times output gradient. And if that's not clear, I would tell you to just revisit the previous lecture. So that's multiplication here. Similarly, for subtraction, things would be almost the same. We can just copy this and paste here. Since it's A minus B, this will turn it to minus because we are subtracting. And that again comes from the formula that we derived last time. So this looks great. Okay. So now I think we have a good idea how to calculate gradients. Now the next goal is to calculate a graph so that we can come back to our children properly. We will use a technique called topological sorting. And topological sorting is an algorithm that you can look online, but what it essentially does is it helps us to revisit our nodes in the reverse order in which we added them. So if we added the nodes as A, B, C, it will let us come back to our nodes as C, B, A. So we need to find a way in which we can do that. Our main goal is, let's say that we have this graph, and let's say we also have some complicated things like we do C, and then we also do C plus, and then from D we do some other operation, and ultimately we calculate this value L. So we need a way in order to create a graph. And the theory behind creating a graph is, once we created the graph, we want to revisit the nodes in the reverse order. So we want to use L and then go back to its children. So the children of L in this case will be C and D. We want to go back to the children and then calculate the gradients of the children and then go backwards again. So then C will again go back to its children, A and B. And it's kind of a recursive thing that we just keep on going backwards and backwards. Let's look at a backprop function. What does it do? So backprop function does a lot of things. The first thing is calls a function called buildTopo that we will just build. And the responsibility of buildTopo will be to build a topologically sorted graph. Once it does that, then it will visit all the nodes and call its respective backward function. So for example, if let's assume we have filled this topo data structure, now we will just do for nodes in topo, nodes backward. So it will keep on going backward, backward, backward and calculate the gradients of each node. So now's the main thing, how to create this buildTopo function. So as I said, we will be dealing with shared pointers. So the first argument of buildTopo has to be the current node because we need to go backward from this node always. So for that, we need to do a concept called shared from this, and shared from this creates a shared pointer from this. And that's only possible because we have derived from this enable shared from this class. If we didn't derive from this, we couldn't have used shared from this concept. So it will get this shared pointer. And creating a graph, we also need to have a set so that we don't revisit the nodes again and again. So we need to create a set that is called visited. And I'll just do it like this. Apart from that, I think that's basically what we really need. So Build topo function will be very simple. What it will do is it will get the current value. It will also get that visited set, and it will also get that topologically sorted vector. That will be a graph. It will first see if the current value is already in visited. If it's not visited, then we will insert it in visited, and then we will look at its children and then call this function again and again. So it will create this topologically sorted graph. One thing that I need to mention is, since we're using unordered set, we need to implement a hash function for this to work correctly. We will pass in visited. We will also pass in topo. Okay. So creating a hash function can be done in different ways. One of the ways is like this. You just define a functor that takes in a shared pointer of value. That is value pointer. You can just replace it like this. And it returns a size t. And now let's try to implement it. So again, you take a value pointer and you use all that information to return a hash. You can successfully insert nodes into this visited unordered set. Topo function. Now, once this graph gets created, you need to use that information to calculate gradients. So let's look at L now. Let's say we have already created the graph, and it might look like A, B, C, D, L, something like that. And now we want to use this information L and go backwards. So first of all, what should be the gradient of L? That's a great question. So dl with respect to dl will also always be 1. So we will use some iterators to achieve that. And we can achieve it like something like this. So we will start from the rear end of the data structure, that is L. And we will keep going on backwards. And right now we haven't defined this. So let it like that. And we can just call the print function of the iterator. Something this, and this should work. So let's try compiling it now. We will need to install some headers for that. First is another set, and second thing is we also need to do std string, and I'm just trying to find where do we want to do std string. Yeah, here. And we'll do std hash, something like this. Let's see. It works now. Still not. Std vector is 6. Okay, so we have this working. Now let's try it and see if we get the correct value. So let's say we have d, and let's say auto L is equal to, we have d, so let's say value dot add d with d. So let's say this is our final loss function, a loss value, and let's say we do loss prop. So we do backprop on loss. That means that we will create all this topologically sorted order, and we will also do this gradient business here. So let's compile it and see what do we get. So A and B gives C. C should be 3. D is C times C, that is 9. And L is D plus D, that is 9 plus 9, that is 18. when we do loss.backprop, L is 18. So the gradient of L with respect to L is 1. And then we will, from L, we will go to D, and D's value we calculated was 9. D's value is 9. And its gradient is 2. And then we will go to the data 3, that is C, and then B and A. So 2 and 1. So this is a simple backpropagation algorithm that we just implemented from scratch. And this is part 2 of this lecture. There are more lectures to come. I just want you guys to just wrap your mind around this. Take time to understand it properly. Take time to tweak it, and I will see you in the next lecture. Also, it takes a lot of time and energy to research and make such videos. I will highly appreciate if you can please like and subscribe this video so that I know that you guys are finding this really valuable and I can keep making such videos. Thank you.